This lesson is on differential equations and slope fields. Now, these are two topics or ideas that we have touched on in previous sections, but now we're going to just really focus on differential equations and slope fields for one section. That's all we're going to work on. A differential equation is an equation with x's, y's, and derivatives of y in that equation. So dy dx equals 2x is a differential equation. So once we started integrating, we worked with differential equations since then. And you saw in some of the problem sets some slope fields that you had to work with. Those little graphs where at each point there was a little hash mark that represented the slope of the curve at that point. So, we're going to start with differential equations, like I said, involving x, y, derivatives of y. Some vocabulary. The order of a differential equation is the highest power derivative in the equation. It's similar to the degree of a polynomial. You look at the differential equation, y prime plus 2y equals 0. Well, the highest derivative you have is a first derivative, y prime. So this is a first order differential equation. You look over here, you have a 2xy double prime minus a y triple prime plus an xy prime equals 0. The highest derivative you have is a third derivative, so this is a third order differential equation. Different order differential equations have different applications and uses that you'll learn probably more towards Calc 2, but this vocabulary is important to know. The solution to a differential equation is the original equation that makes that differential equation true. Differential equations can have more than one solution. And it's kind of like the original equation when you anti-derive. The original equation makes this true, except some of these differential equations, especially in this section, get a little more tricky than just a quick dy dx equals 2x minus 1 or something like that. You have more than one derivative in there, x's and y's. But the solution is still the original equation that makes the differential equation true. So the original equation, when you took its derivative plus 2 times the original function would equal 0, in this case, would be the solution to this differential equation. So you have y prime plus 2y equals 0 is y equals e to the negative 2x, a solution to this differential equation. Notice it says a solution, because there can be more than one, but they want to know, is y equals e to the negative 2x a solution? Does y equals e to the negative 2x make this differential equation true? So the first thing you need to do is find y prime, because you have a y prime, a first derivative, in this differential equation. So y equals e to the negative 2x, y prime equals negative 2 e to the negative 2x. So we know what y prime is. We were given y, so now you substitute in and see if this is true, if both sides of the equation are equal. Y prime, negative 2 e to the negative 2x. Plus 2 times y, plus 2 times e to the negative 2x equals 0. Plug it in and check. Does this plus this equal 0? Yes, it does. So yes, y equals e to the negative 2x is a solution to this first order differential equation. Similar to antiderivatives, you have general and specific solutions to differential equations. The general solution is the one that stands for numerous solutions, and it involves unknown constants, usually represented with a c or a k, or in some situations you'll see it's represented with both c and k can occur in certain differential antiderivatives or differential equation solutions. And a specific solution is one where you solve for the constant by substituting some initial condition. And you've worked with these ideas back all the way from chapter 4 when we found antiderivatives with a plus c at the end, and then sometimes we had to find c. Same idea here, except with some more complicated differential equations. So another example. Determine whether the function is a solution of the differential equation y double prime minus y equals 0. So here's our differential equation. Y double prime minus y equals 0. So it's a second order differential equation. and whether the function, so here's the function they gave you, y equals cosine of x. Is this a solution to this? Y double prime minus y. So we have y, we don't have y double prime, so we have to derive this twice. Y prime is negative sine of x, y double prime negative cosine of x. Now we have all the things we need to substitute and check to see if this is a solution. Y double prime, negative cosine of x, minus y, cosine of x. Negative cosine x minus cosine x equals 0. Well, that's not true. So it's not equal, so no. Y equals cosine of x is not a solution to this differential equation. Some of the differential equations you work with will get more complicated. There'll be a lot more algebra involved, but the idea is the same. Find all the derivatives necessary, substitute them in, and see if they are algebraically equivalent on both sides of the differential equation, if the left side is equivalent to the right side. If it is, then that original equation was a solution. If it is not, then it was not a solution to the differential equation. Slope fields. Again, you should be familiar with what they look like. You've seen some, haven't worked too much with them to this point though. A slope field is a way to get an idea of what the original equation, what the solution to a differential equation looks like when it's either very, very difficult to find what the original equation is algebraically, or it's impossible if we don't know how to integrate, how to anti-derive the specific differential equation that was given to us. So that's when a slope field is useful. If I say dy dx equals 2x, well, you know the antiderivative is y equals x squared plus some constant. So a slope field doesn't really help us, so you know what a parabola looks like. But if we have some function, y prime equals f of xy, meaning it's a function in x and y, so you have x's and y's equal to the derivative, then sometimes or oftentimes it's either going to be easier to sketch a slope field and see what that is, or it's the only option to see what the original or the solution looks like. All right? And these are the top kind of derivatives that you would have seen back when you used implicit differentiation, where you multiply by y prime or dy dx, solve, got everything equal, and you had x's and y's on the one side. So these are the complicated derivatives that you solve in, and oftentimes they're used to find slope fields, or slope fields are used to get an idea of what they look like. So we're going to start with some relatively simple ones so you get the idea of how to construct or how to create a slope field. So this asks you to sketch a slope field for the differential equation y prime equals x minus y at the given points. So this is a derivative, y prime in terms of x and y. It matters what the x point is and what the y point is in order to determine the value of the slope of the curve at that point. So these are the points, negative 1, 1, 0, 1, 1, 1, 2, 1. So in order to find the value of the derivative, the value of the slope of the tangent line at that point, we use y prime equals x minus y. Negative 1 minus 1 is negative 2. So the derivative at negative 1, 1 is negative 2. Derivative at 0, 1 is negative 1. 1, 1 is 0, 2, 1 is 1. You just plug in x and y into the differential equation to find the value of the slope at that point. So there are the values of our slopes. So we'll go over here. Little graph. At negative 1, 1, your slope's negative 2. So at negative 1, 1, your slope's negative 2. So what you want to do is you want to sketch a tiny little tangent line at that point with the given slope. Negative 2, I want to be going down at more than a 45-degree angle. And you just draw a little sketch, a little line, little segment. At 0, 1, my slope is negative 1. 0, 1, going to have a 45-degree angle. And you see, this is more negative than this. 1, 1, you're going to have a slope of 0, so you're going to have a horizontal tangent line. And at 2, 1, you're going to have a slope of 1. And there you have the values of the slope field, or the pieces of the slope field at those 4 points. Now, a slope field is constructed by doing this at every point. Normally, you won't have to do more than, 5 to 10 total points in a problem, just to show that you can evaluate them and draw the little tangent lines appropriately. This is often a question on the AP test. Often they'll give you a small little graph and they'll ask you to sketch a slope field at the given points, usually somewhere between 6 and 10 points, somewhere in that area. They're not worried that you get out a protractor and a ruler and make this perfectly a slope of -2, this a perfect slope of -1. They are worried that relative to each other, that you can see, this is -2, so I know it's going down at more than a 45-degree angle. This one's -1, so it's going to be going down, but not as much, not as fast going down. Slope of 0 has to be a perfect horizontal tangent. Slope of 1. So they're more worried when you're assessed on this, when I assess you on this, we're worried about obviously the right sign, going up or going down, if it's positive or negative, and the steepness as compared to the other ones. You know that it's getting steeper as you go across or as you go up or down. And you'll see that the more you practice this. Alright, another question, we're going to sketch a slope field. Sketch a slope field for the differential equation, y prime equals 2x plus y, using the points in this table. So x, y, y prime, -2, -1, -2, 1, -1, -1, -1, 1, 0, -1, 0, 1, all the way down to 2, 1. What I'd like you to do now, pause this, take some time, fill in this table. Find the value of the derivative at each of these points using this differential equation, y prime equals 2x plus y. Okay, hopefully you filled that in. Now in the next graph or slide, here are your values. -5, -3, -3, -1, -1, 1, 1, 3, 3, 5 as you go across. Now the instructions are going to be 2 parts. Use the table to sketch a slope field for the differential equation. So again, I'd like you to pause, get out a sheet of graph paper, or just sketch a graph. Plot these 10 points and sketch small little tangent lines at each of them. So you're going to have a slope field consisting of 10 little segments. Alright, hopefully you have that slope field constructed. Should look like this. Really steep here, not so steep at these two, less steep at these two. Going up here, going up steeper here, going up even steeper here. Alright, so there's your slope field, and again, it's just relative to the others. Now, the second part of this question. Use a slope field to sketch the solution that passes through the point 1, 1. So that's why I have the point 1, 1 here. So, using a slope field, it tells us what the function's doing at those points. I know that my curve is going to go through 1, 1. I know at 1, 1, the curve is going to be going up. Going up to the right, going down to the left. Now, as you see, as I start going down, at some point in here, the curve is going to be going from increasing to decreasing, from going this way to this way, and then coming back up slowly. So, we want to kind of sketch this. There's no exact science for sketching a slope field, for sketching a curve using its slope field, but you should be able to get relatively close. So I'm going to be going down, turn around somewhere in here, come back up. So I'm going to shoot this up there, come down, come back up. So it's going to be a curve that looks somewhat like a parabola. Not a perfect parabola, but something like this. You'll do plenty of these in class to get some practices to how to do this. It takes a lot of practice just trying and, getting close and making mistakes and seeing, oh, okay, I understand. Now by looking back at the slope field and seeing where things turn around, where things are going up, where things are approaching an asymptote, things like that. The majority of the time when you sketch from a slope field also, you'll have way more than just 10 little segments to work with.